All right, recording has started. And HelioPy, our first speaker, please take it away.
Hello, I think you need to stop sharing your screen so I can share mine. Yes, great, thank you. So whilst I get this set up, hello everyone, so I'm David Stansby. For those of you who don't know me, I'm at the Mullard Space Science Laboratory at UCL in the UK. And I'm gonna talk. It's gonna be pretty brief, but I'm gonna talk to you a bit about the status of HelioPy. So I'll just give a quick reminder of what HelioPy does, and then a little status update. So HelioPy, since the last meeting have kind of given it a I guess a mission statement that it's Python for 1D in situ time series. It's kind of specifically for 1D stuff. So, magnetic field measurements as a function of time, plasma parameter density, stuff like that as a function of time. And tools to search, find, download, and analyze that data. So it's a fairly mature package. It's got extensive documentation and code testing, and it kind of basically comprises of two sub-packages. So there's the data sub-package and there's the spice sub-package. The data sub-package contains functions for basically loading data into Python. So the way it's structured down here is there's one sub-module for each spacecraft, so they're listed on the right there. And then for each data product, there's one function. And you call this function between a start time and an end time, and there can be other parameters like I guess data level or other parameters depending on the data product. But this essentially will automatically download and cache the data, and then return the data to you in a variable which I just called data here. As you can see, there's quite a few different instruments supported at the moment to various levels in terms of the data products available. And so the way it's structured, it always returns a SumPy time series, or generic time series is a specific name. And essentially this is just a wrapper around Panda's data frame and AstroPy units. So we kind of get all the benefits of Pandas and their advanced time series manipulation, but we also get units as well. So you can see here, if I plot an example time series, this is from Parker Solar Probe, and I just plot the BR quantity, so the radial magnetic field. The units of nanotesla are automatically recognized and they appear on the plot. That's kind of how the data module works. The other main module is Spice. So for those of you who don't know, Spice is, I guess it's an acronym, but I don't know what it stands for actually, off the top of my head. But it's essentially used for generating, or among other things, is used for generating the trajectories of spacecraft or planets or generally bodies in the solar system. And so this is essentially the HelioPy.spice submodule is just a higher level interface to SpiceyPy, which is a really nice kind of one-to-one translation Python implementation of the SpiceC library. So in HelioPy we have these classes, so a body which represents the body, so that can be a spacecraft, it can be a planet, it can be the sun, for example, and then an SPK kernel. So these are the files that basically tell Spice how to generate trajectories, and then a trajectory class which represents an actual trajectory. So just an example use here is we'll create a trajectory for Parker Solar Probe. So SPP is its old name for anyone who remembers that in the pre-Parker days. And then we can generate positions. So times here would just be an array of times relative to the sun and in a given coordinate system. And then kind of nicely, this integrates with the AstroPy coordinate system with help from SumPy. So we can get a sky coordinate object out here. Okay, so those are the two main parts of HelioPy. I haven't really worked on them much, which I'll talk about in a couple of slides, but one thing I did want to quickly mention, which is a bit of a tangent, but I thought I'd use the opportunity, is a set of examples I'm putting together for Solar Orbiter. So now Solar Orbiter is about to begin its science mission. I'm putting together a collection of scripts for common data analysis techniques using Python packages, including HelioPy. So I just thought I'd point that out. If you want to add stuff, like, you're very welcome. There's no requirement on specific packages or anything, apart from they have to have stable releases. So this is just a new project I've started to try and basically help people who are trying to get their hands on Solar Orbiter and how to analyze the data. Cool, so to finish, the current status. So HelioPy is currently hibernating. So as I said, I haven't really worked on it much for the last year, and that's for a couple of reasons. So I only really personally have interest and time to work on Parker Solar Probe and Solar Orbiter related functionality. So one question I wanted to ask, since we're here, is the support for other data sets, so like planetary magnetospheric stuff elsewhere, that perhaps HelioPy could drop and I guess leave to other packages to implement. And also there's no funding. So as far as I'm aware, there's no kind of UK funding for these things. So I'm based in the UK and there's no kind of equivalent of the NASA HDE funding. But if anyone knows, I'd love to know. And then I kind of have future plans, but as I said, I don't have loads of time at the moment, so they're on hold. So I'll stop there. And yeah, if anyone has any questions, let me know.
Hi, David. Nice presentation. This is John Vandergriff. I have a quick question. How do you get the units? Are those hard coded in, or because not every data set has a consistent AstroPy flavored strings or whatever?
Yeah, so if we're loading in a CDF file, CDF files often have the units in, but if it's an older like text file, say, that's done manually per data set. Yeah.
Yeah, but even in CDF, the strings they use may be, I mean, NT, hopefully that's what they use, but they might use different approaches. So
Yeah, so essentially we have a big mapping from different like non-standard unit strings to a standard set of unit strings, which does the job most of the time. Yeah.
yeah, what we're trying to encourage people to do is to indicate what family of unit strings they're using. Like, are you using AstroPy? Are you using, there's one that Cluster used, anything that's documented online. If you can indicate, hey, my unit strings all come from this framework, then you could know which dictionary to use, for example.
Yeah, okay. And I'm not aware if there is like a standard out there for unit strings. I think there might be, but I don't know if anyone knows anything more about that.
I mean, there's multiple ones, I guess. Because I worked with the Happy specification to try and come up with a way to describe time series data, and we didn't require anybody to have a specific unit strings, but we just were asking people, oh, if you know that your unit strings all come from this set of conventions like AstroPy, then you can specify that. These are all AstroPy unit strings.
Cool.
Other questions?
Yeah, I'd be particularly interested if anyone knows about or what software people use for magnetospheric or planetary.
I think you're going to be hearing about that in the next few talks.
Okay, great, cool.
That's correct.
Awesome.
Well, if we don't have any more specific questions, then we can save some time for discussion later and move on to Plasma Pi. I
Sure.
take it that is Nick. Excellent.
Let me
Yeah.
share my screen.
That sets us 4 minutes ahead of schedule. Look
Ooh.
at that.
Cool. So, showing up okay?
Yep.
Crystal clear.
All right. So today I'm going to talk, give an update on Plasma Pi, which is being developed into an open source core Python package for plasma research and education. So to give a bit of context, plasma science is fundamental to all areas of heliophysics. And the reason why is that the heliosphere is mostly plasma. And in addition to that, there's a cross-disciplinary aspect too. We can use laboratory experiments to help us understand heliospheric processes. And heliophysics allows us to study plasma processes in detail, in situ, in particular in regimes that we have no chance of getting in the laboratory. So we need plasma physics functionality for a software ecosystem for heliophysics. And Plasma Pi plays an interesting role where we want to be a core package for plasma science, and also be one for heliophysics too, for PyHC. So the overall goal of the Plasma Pi project is to grow an open source software ecosystem for plasma research and education. And to do that, we're following the model of AstroPi and SunPi, of having a core package which contains the functionality that is most needed by the broader plasma science community. And it's currently under active development. We just had our 0.6 release within the last 2 months. And we also are planning to have affiliated and community packages that will contain more specialized functionality. So things that are needed by a particular specialization or subfield within plasma science. And most of these we plan to have to be created by the broader plasma community. We also want to have educational resources that can be used in introductory plasma physics courses. And we want to be able to introduce plasma physics concepts using Plasma Pi. So be able to introduce students to both of these at the same time. We also, the community aspect is important. Since we're here for the Python Heliophysics community meeting, we already get that. And to do that, we've had informal online community meetings for a while. And also we've been trying out virtual office hours once a week. And we tend to have maybe like one person stop by per week. But we plan to advertise that a bit more. And of course, we also have a code of conduct. So to give a quick overview of our subpackages, the first one is plasmapi.particles. And this subpackage includes functions related to getting information about particular particles, as well as the particle class, which allows an object-oriented representation of the different particles that show up in a plasma. And this is pretty important because it turns out that plasmas tend to contain different particles in them. So if you want to write a function for the alphane speed, you need something to get the, for example, the mass of the ion. The next subpackage is plasmapi.formulary, which includes the things that come from, if you know, the NRL plasma formulary. So things like the alphane speed or lower hybrid frequency or Debye length, all sorts of fundamental plasma parameters like that. And to do this, we build on AstroPi.units. We're also in the process of developing plasmapi.simulation, which includes a particle tracker. And our goal is to have this include the building blocks of plasma simulations. And we're hoping to start a simulation working group within Plasma Pi in the next few months. Two of the packages that have undergone a lot of development over the past 6 months are plasmapy.analysis and plasmapy.diagnostics. And the analysis subpackage includes analysis techniques for data from different sources, simulations, experiments, and observations. And diagnostics is for representations of plasma diagnostics, including Langmuir probes, magnetic flux probes, and various sorts of things like that, as well as the ability to create synthetic diagnostics. We also have a dispersion subpackage, which I think was new in 0.5. And we're developing this to contain dispersion relation solvers for plasma waves and instability. So this is one potential big area of overlap with other PyHC packages. And then our plasma subpackage is for including base classes to represent different plasmas. That is also under development. So since the last PyHC meeting, we've been trying to have more frequent releases, like a 3 to 5 month cadence. And so we had 0.5 at the end of last year, and then 0.6 in March of this year. Another fun thing was that we organized a mini conference at the American Physical Society Division of Plasma Physics meeting on growing an open source software ecosystem for plasma science. And for this, we had a lot of different projects represented. So particle and cell codes, some talks for the limited number of metadata standards in laboratory plasma science, and a lot of other projects that are working to build this collection of open source software for the community. And our goal was to get us talking to each other. The virtual format didn't really allow it, but we had some follow-up discussions afterwards. And the biggest advances that we've had in the last 6 months have been in plasma diagnostics, in particular with laboratory plasmas. So things like Langmuir probes, Thomson scattering, and some really cool proton radiography functionality. There's a Jupyter Notebook in our documentation page. Well, I think for most of these. So there also have been some challenges between the March 2020 that was in March 2020 and the March 2020, which is still happening now. And of course, there's what I tend to call the pandemic era brain blah. So probably all of us have noticed that it's harder to begin and complete tasks. And so we've tried to be understanding with each other when some of the tasks end up falling through the cracks. And also, it's been harder to welcome new contributors into the community. And we planned our inaugural workshop to be last April, but ended up having to cancel it. And we've also not really had in-person visits and the informal discussions at conferences. But we are planning a Plasma Hack Week, which will happen in a month and a half, June 28th to July 2, which we're, of course, holding virtually. And if you want an excuse to surf the web while or during my talk, you can go to hack.plasmapy.org. The registration page is up there. And we're trying to model this on Astro Hack Week. So to have this be a combination of a summer school, so things like tutorials, probably a couple tutorials the week before that introduce Python, and then tutorials during the week on like Git and GitHub, how to contribute to an open source package, and how to use different packages. Then we have 2 hours of tutorials and structured events, and then a social hour and a 2-hour hack sessions each day. And having it be limited to a few hours per day is to help prevent Zoom fatigue. And in contrast to a hackathon, our main goal is educational, to help provide an opportunity for members of the Plasma community to learn how to contribute to open source projects. And it's one of the challenges while we're organizing this is that few of us have organized an event like this before. And we're hoping to be able to learn from this event to help us prepare for in-person events, which hopefully will happen next year. All right, so some final thoughts. And we do have one good reason to be optimistic in particular, and that's that Plasma Pi is getting better known in the Plasma community. We spent a lot of time in the last, especially 2019 and early 2020, advertising Plasma Pi during some efforts to develop community-wide plans for plasma science. And so we are noticing that it's getting to be talked about. But with that said, we do need to expand the contributor base and provide more ways for contributors to become involved. And we also still have a lot of functionality to add in the coming years. And we also have, which I'm happy to talk with people about further, a lot of potential areas of future collaboration between Plasma Pi and other PyHC projects. So things like plasma pi dispersion, waste represent particle distribution functions, time series turbulence analysis tools, simulations, and education and training. And I probably have several more topics up here too if I didn't end up preparing this talk at the last minute. But yes, we're happy to talk with you further, any of you, about collaborating. So that's all I have. So any questions?
Yeah, hi, Nick. I've got some, if you don't mind.
Oh, sure.
The particles class, when you represent a particle, sometimes in data we get weird ones where it's like, oh, this is heavies or CNO, or, you know, it's a range of things. And we've always kind of fudged that to try and get it to work. What do you do for cases like that?
There are a couple of things that we can do. The first, we have a custom particle class, which we can provide a mass and a charge to a particle, and it'll behave a lot like a particle. We created that fairly recently and still have to make it fully functional within the formulary. But that's one way to do it. The other way, we have classes that represent the ionization state of either ions of a single element or ions for multiple elements. And with those, we can put in the ionic fraction. So if it's like 50% singly charged helium and 50% alpha particles, then we can record that. So we do, and then also we have a dimensionless particle class, which we expect to be mostly used for dimensionless simulations.
Okay, yeah, it's just if the measurement technique doesn't distinguish which exact particle it is, I guess I guess you have to expose that to the users and let them choose, okay, what are you going to assume that this is? Or yeah, it's hard to represent that in these kind of standardized approaches. I'm just trying to see what you've done with that.
Yeah, if there are like common techniques for doing that, then we could implement those, but probably that is going to be on the user side, since they know what the particular instrument or data set, like the
Right.
conventions and assumptions there. But yeah, that's a good question.
And I had another question about who were the folks that showed up at your office hours? Was that early career, mid-career, late career?
Mostly early career. So there's an undergraduate at Bryn Mawr who's doing a project developing a plasma formulary online calculator. So she sometimes stops by to get feedback. There's another undergraduate who occasionally shows up. We've had a few graduate students show up, and then once in a while, a mid-career researcher. But yeah, it's mostly been early career students and scientists.
Mm-hmm.
And you can get the information for the office hours on our website. They're currently 2 to 3 on Thursdays Eastern time.
I've got a
Oh.
question.
Mhm.
Yeah, just curious where the idea to have your own mini conference came from.
Oh, that's a good question. I think in 2018, there was a mini conference on data science in plasma physics. And that, I think, was what sparked the idea for ours. But at the APS-TPP meeting, there tend to be like 4 to 6 mini conferences per year. So it's kind of like a standard thing that happens in that.
Okay. Neat.
Yeah, it didn't really lend itself to informal discussions, unfortunately, but we were able to give a chance for us to learn from each other. Anyway.
Yeah, fair enough.
All right. In that case, I'll stop sharing and the next person can go. Thanks.
And I believe that next
Yes,
person
we're
is
hearing
me,
Now we've got Space Pie.
Space Pie. Okay, hopefully you all can see my screen. Oh boy, and Zoom puts everything in the way. I'm gonna put that in chat and close that. Hi, I'm Dan Welling from the University of Texas at Arlington and one of the developers for Space Pie. And today I just wanted to give a status update on behalf of the Space Pie team. So that's of course John Niehoff, Steve Morley, Brian Larson, and myself. I'm going to zip through these slides. I think I have probably more than I need to say, but that's okay. I wanted to start with introduction of Space Pie and what it is. So it's an open source library under the PSF license. And Space Pie is a toolkit and a library and not an application. So it was really developed with the idea that we all have a bunch of space science related tasks to do, but at the time we made the library, very few options for how to do this in Python. And so we developed a toolkit in Space Pie to help overcome that. That is now 11 years ago. So Space Pie is finishing up the 5th grade. The focus is really on magnetosphere, ionosphere coupling, with some heliosphere. It's matched the developers' research interest, and that's now starting to include those from the broader community through pull request and other contributions. And development is really need driven. It's driven by science requirements, data set production, what we need to do in our research in terms of data processing, model output processing. And I want to emphasize that it's not just the developer's needs, but rather with more pull requests and more input, trying to answer the needs of the community more and more. So as kind of a general example of what you can do with SpacePy, take this example of where you're trying to examine distribution functions from the Van Allen probes or RBSP satellite in context of observations from Themis and observations from LANL geosynchronous. SpacePy comes in a whole lot of steps here, from reading the data files via PyCDF and placing it into a data model, which is our class for organizing data sets, to plotting the data. Of course, there's always the issue with coordinates and whatever data set, whatever coordinate system each data set is in, the coordinates module can help you change from different coordinate systems. We have a lot of plot utilities in the appropriately named plot module, including a matplotlib style that increases the default font size, sets the background to this the gray and white scale back there, sets colorblind friendly colors and color maps, and has a whole lot of convenience functions like placing a day-night Earth into view like so. Boink, I'm gonna hit the wrong button 10 times today. When it comes to actually calculating data products, you can get, for example, in this plot, we're looking at the distribution function for a given mu k from the different satellites as a function of L star. And we want to place that in context of the state of the magnetosphere in terms of KP and DST over here. So you can get L star via the LANL star module, magnetic fields from, including the Saganyenko models from the UrbamLib library. The plot module, of course, has a whole bunch of tools for making these kinds of plots easier. You can fetch DST and KP from the Kyoto World Data Center website, and making a plot like this at the bottom with the traffic light green, yellow, red KP is like a one-liner in the plot module. So it's a lot of things to make space science easier. But it's even more than this. We have access to empirical models like the Xu et al. Magnetopause model, AE9, AP9 models, access to the OmniWeb database. When you install SpacePy, it will actually fetch the hourly Omni data from the web, including the Kin-Denton values for calculating Saganyenko model values. And it's possible to change that to minute level data if you pull it from the right spot. We have our own time module to handle the intricacies of handling time in space, including leap seconds. My favorite module, of course, is PyBats, which is an interface for handling output from the space weather modeling framework. So this is the University of Michigan's Bats R Us coupled to the ring current, coupled to it's a whole bunch of models all coupled together there. Things like CPy, which is superposed epoch analysis tools, and there's even more than that. Central to everything is our data model. So SpacePy was put together before pandas and before a lot of some of the more modern Python tools. And we were facing the problem of trying to organize rather complicated data sets. And so, enter the data model. It reflects capabilities within tools such as NetCDF or HDF or even NASA CDF files. And what I mean by that is that we have two important classes that we use. The first is DM array, which subclasses NumPy arrays, but adds this adders object attribute. And this allows you to store attributes about the data stored in that array, for example, units or coordinate system or more. Then we have the space data object or class, which subclasses dictionaries and allows us to organize DM arrays together and have global level attributes. So the net result of this is that data sets are handled like dictionaries, which is very comfortable for Python people, with these adders object attributes to contain both global and variable level info and allow us to organize things and keep track of things a little cleaner than you normally would. And this is standardized throughout SpacePy. So if you know how to handle a data model object, exploring an unknown data set, figuring out what the variable names are, what the attributes are, is very easy to do. It's also central to how we handle different file formats. And when you open an HDF5 or JSON headed ASCII or an SWMF formatted binary file, the first step behind the scenes is placing it into the data model, and then it's really easy to change formats via the methods inside the data model. So I can really easily turn an SWMF binary into an HDF5 or a JSON headed ASCII, etc. So what's going on with SpacePy? Quite a bit. We've had 95 pull requests since the start of 2020, which is a lot, and we're working very hard to try to work through and approve as many as possible. One of the big things that we've dealt with is our continuous integration. As many of you know, Travis CI had a fundamental change to their cost model, making free use of this tool not free. So we had a switch to GitHub Actions to keep our CI working. And I really want to take a second to recognize the effort by John Niehoff to make this happen. I mean, he's a one-man army working on these things. So thanks, John. We finally released version 0.2.2 right at the end of the year. And I'll talk more about that in a second, but one of the effects is that we've updated our dependencies. So now you have to be running at least NumPy 110, SciPy 0.11, and Matplotlib 1.5. And there's a lot more details in the change log. We're working a lot on right now on version 0.2.3. One of the main focuses here, foci, is expanding our test coverage as much as possible. But with that, there's going to be cool new features as well, and I'll show you some examples of that. 0.2.3 is going to be a bit of a goodbye party for some things, namely Python 2 and 32-bit Windows binary installers. And I hope that doesn't affect too many people here, but it's good to pay attention to these things. As we transition out of 0.2 and into 0.3, we're going to be dropping Python 2 support. There's some details here, but if you go to the repository, we have our end of life wind down very clearly spelled out in this file in the documentation. So definitely check that out if you're worried about Python 2, but we're going to be winding down on that quite aggressively in the near future. 0.2.2 has a host of quality of life improvements in terms of updating the upstream urbanlib library to revision 620. This gives us more up-to-date IGRF coefficients as well as some other things. Improvements such as allowing spacepy.coordinates and urbanpy to support using all of our coordinate systems as inputs to routines to make that kind of approach easier. Our TikTok class, which is our base time class, now supports conversion to and from AstroPy time class. So this is our first foray into interoperability with AstroPy. Hey, here's something that I find really motivating. We have a new convenience function in Plot called add arrows that allows you to add arrows to lines. So how many times have you wanted to plot a streamline in Matplotlib and distribute some arrows along them, or a magnetic field line just to indicate direction? That's now a one-liner inside of Plot that you can take advantage of. We also have a bug fix for time conversions for times before 1961 so that we're using the proper number of leap seconds. So a small bug fix, but an important one if you're using older dates and times. John Niehoff really dedicates himself to keeping the PyCDF library up to date, powerful, and complete, and I really want to compliment him on that. There's some new improvements here that we should all be paying attention to if you use this library. Notably, it now supports variables with sparse records, and you can set the pad value in those sparse records. And we really want to recognize the PR from Antoine Brunet making this possible. Thank you very much. as we move to version 0.3, there are going to be some changes in the default behavior of PyCDF. And as we transition to those changes, we're introducing new warnings to help ease that transition. Specifically, if you create a new CDF file without indicating backward compatibility, you're going to get warned. The default is to make backward compatible CDFs, but this is changing in 0.3. Similarly, if you create a time variable without specifying a time type, you're going to get a warning. Right now, we use epoch or epoch 16, but this is changing in the future. So heads up on those changes there. Being an SWMF guy, I get really excited about updates to PyBats, which is the sublibrary for handling space weather modeling framework output. The standard output file for the SWMF is this star.out file. And what happens is that you run a global magnetohydrodynamic coupled simulation and you set how frequently you want these output files. Okay, I want a 2D slice every 60 seconds. I want virtual magnetometer arrays every 5 seconds. And over the course of the simulation, you wind up with dozens, then hundreds, then thousands of output files, depending on how long you go. A 48-hour run, for example, is not out of the question. The SWMF for a long time has provided post-processing tools to concatenate all of these binary files to cleverly named .outs with an S files. Now, this is a huge convenience in some ways, but it leads to a really huge file. And SpacePy just hasn't supported this, this change because there's some challenges associated with that. But I'm very happy to report now we do. What happens is that upon reading either an out or an outs file, SpacePy flips through and figures out the number of frames, a frame being 1 epoch worth of data, and catalogs the runtime, date time, and iteration of each of those frames within the file, and only loads one at a time because these files can be tens to hundreds of gigabytes large depending on the nature of the output and the size of the run. So it defaults to the first one in the file, but you can change that via keyword argument. And then we have a method called switch frame that allows you to navigate through the frames. And one of the cool features that we worked on to make this work better is how do you handle derived values? So for example, in these files, you're going to have an MHD output BX, BY, BZ, but you might want to calculate the total magnetic field B. Well, when you switch frames, you're loading new data and the data file only has the components, not the calculated derived variable. So what we did is we created a Python decorator wrapper for any function or object method, I should say, that begins with calc. And it keeps track of what values you've calculated and updates that every time you change frames. So to give you an idea of what this looks like, let's suppose that you wanted to plot the first and the last entry in one of these files. You start with your
Hey,
imports.
Dan?
Yep.
Just, we're running short on time a little bit.
Oh
so
no, okay. I'll
I
skip
know,
through this.
sorry.
No, it's okay. It's my fault. This works easy, trust me. We're updating our standards and for our style standards, so expect that in the future. A lot of arguing on our ends, but we're working on it. And we're updating the coordinates backend. Long story short, this is laying the groundwork for further interoperability with AstroPy. 3D PyBats is in the pipe. I want to end with this cool movie. We're looking at this is an adaptive mesh automatic refinement run in the space weather modeling framework. And down here we see the adaptive meshing, and we're looking at the currents in the equatorial plane. Making this animation in SpacePy is like 25 lines, and that includes like setting the folder and the output file names and all that crap. It's actually not hard to do this, but most users don't know the right methods to make the job easy. Our docs are very specific. We really need some high-level tutorials. So I've posted an example of a high-level tutorial on my rather new blog trying to cover some of this stuff. But our hackathon later this week is going to try to cover that. So if you want to either learn how PyBats works or contribute to some tutorials, please jump on board and join me there. And I'm sorry for taking up so much time. Any questions?
Yes, I have a quick question if that's okay. I also have a suggestion. For 3D stuff, we're going to do that in SunPy this summer with a student, hopefully. But we're going to use PyVista. I don't know if you've heard of that package, but it's kind of a nice Pythonic interface to VTK, and I would recommend. And my quick question was, so correct me if I'm wrong, but you don't have like, users have to download the data they want first, and then Spacify Pi kind of deals with reading it in. You don't have like any search or download tools.
That is mostly correct. The exceptions are the Omni module, which will download it for you, the interface to the Kyoto World Data Center geomagnetic index data sets, and there might be another one hidden in there, I'm not sure.
No, I think that's about it. At some point, honestly, I'm just going to throw up my hands, unify those, and bring another downloader into the world, which I kind of hate to do, but it's a also a fairly obvious weakness.
Cool. Yeah, just
Another good one you can extend.
Okay. If there are no more questions, I'll get out of the way.
Let's go to SunPy.
See whether Zoom actually wants to show. Damn it. Okay. I can't share my screen because I've messed this up. I will be back in a moment.
Let's see. PySat was gonna go up after SunPy. Let's give him 30 seconds to a minute to get back, and if not, we might just shuffle the order a bit.
Hello.
Hey, welcome back, Stuart.
Oh, can you hear me?
Yep.
Hello.
Hello.
Oh, good. I can share my screen, but now you can't hear me. It's going well.
We can hear you. Maybe you can't hear us.
Oh, I can't hear you. Yeah, one of the two. There you go. That's better. Okay.
Yep.
I've made choices with my Linux desktop setup that Zoom does not agree with.
Great, we can. Well, I can see those.
Me
Cool.
too.
You can go to this URL to follow along at home if you like. Okay, so I'm going to chat about SunPy. I'm just going to give an update on what's been going on with SunPy and what some of the new things that have happened in roughly the last year are.
Someone on their iPhone needs to mute. There you go.
For people who don't know or have forgotten, SunPy has just crossed its 10th birthday, and it's grown from what was initially one package through to a collection of 8 affiliated packages, a bunch of utilities and things. Like the top repo on there, that screenshot is a blogging library for Sphinx, which is nothing to do with solar physics at all, but it's quite useful, and for some reason we're maintaining it. We, starting with the V10 release that happened a couple of years ago, we've been trying our hardest to release every 6 months, the core package every 6 months, with a well-defined support cycle and feature deprecation policy, how we raise warnings and that kind of stuff. So we're still changing things and improving stuff, but hopefully we're doing it in a way that gives people time to update and move forward. So the main components of the core package are these 4 things. There's also a bunch of other smaller things and probably some stuff that I've forgotten, but a lot of the functionality in the core package revolves around the map class for 2D images, time series that David mentioned, for time series data, which has metadata and unit support that extends pandas, Fido, which is our search and download API, Python API. As I will get onto in a minute, Fido had a lot of updates in our 2.1 release about 6 months ago. It's now even more extensible and flexible than it was before. And finally, the coordinates functionality in SunPy, which builds heavily on AstroPy's coordinates infrastructure and provides frames and transform functions and utilities for dealing with coordinates of things in the heliosphere and around the sun, on the sun, in the sun, etc. This is a little small, but so I'm just going to go through some of the new features in 2.1 and 3.0. We released the first release candidate of the 3.0 version a week ago on Friday. So if you're after any of these functionality, you can upgrade to the release candidate, which is on PyPI. Hopefully we will be doing the final 3.0 release this Friday. So one of the big new features in 3.0 is this draw quadrangle method, which is a replacement for our previous draw rectangle method, except based on new functionality in AstroPy. Draw quadrangle, when you give it the specifications for a rectangle. In this case, we're giving it specifications for a rectangle defined in heliographic Stonyhurst coordinates, and then we're drawing it on top of an image in helioprojective coordinates. The edges of the rectangle are follow the constant lines of latitude and longitude in the coordinate system the rectangle is defined in, and all of this transformation machinery is in AstroPy and Matplotlib. AstroPy provides the Matplotlib with the transformations from pixel to world space, and the lines of the rectangle follow the coordinates. The other thing that landed in 3.0, the other big thing that landed in 3.0 is some improvements to the draw limb method. So a map has a draw limb method. In this example, we have 2 maps. We have a map which is taken from AIA, which is a satellite in orbit of Earth, and we have an instrument on the SDO satellite, I should say, and we have a map from EUVI, which is an instrument on the Stereo spacecraft, Stereo A in this case, and that at the time these images were taken, that was about a 90-degree separation from the Earth forwards. I can never remember which way around they are. So we plot both of these maps next to each other, and we plot both the limbs on both maps, and we generate this plot. So on both the maps here, the white limb is the limb of the sun as seen by AAA, and the red limb is the limb of the sun seen by EUVI. The dotted line segments of the limb are the bits which aren't visible from the image. So the dotted red segment is the section of the limb that EUVI can see, which is on the reverse side of the sun from the viewpoint of AA. These changes to map to make it handle different observers better, and come along with various improvements to SunPy coordinates to make it more observer friendly. Hopefully we're well set up to support analysis from Parker Solar Probe and Solar Orbiter and stuff now, where we can handle both like in situ data, or in situ data with coordinate information attached, and imaging data with knowledge of different observers. Other things that landed in 3.0 in MAP was the ability to auto-align two images on top of one another. So if you are trying to visualize two images, say a magnetogram and a EUV image of the sun, you can now auto-align those together using Matplotlib's p-color mesh functionality, which takes all of the pixels and runs the transform through the SunPy coordinate stack to realign them to the base image. I think that was about it on 3.0. I can't remember.
So I'm going to interrupt you real quick to point out that PySat was going to start now, but we started you late, so we can take a few more minutes.
Oh, okay. I will. Yeah. Other things that I mentioned earlier, Fido, our data downloader, has got some upgrades. Its results objects now are AstroPy table objects, and you can. It's much easier to interact with the return results from Fido. This came about because we now added support for metadata only results from Fido, so it supports doing searches for clients which don't download files, and you can interact with the AstroPy table to get that metadata search results out. So this example is getting metadata from the HEK and all the FITS metadata from JSOC in one example. I mentioned that coordinates had a bunch of things. One of the things that landed in 2.1 for coordinates was the ability to handle velocities based on this functionality having grown up in AstroPy. So this is the velocity of Mars in a heliocentric and inertial coordinate system. It's quite speedy. As I mentioned at the beginning, we attempt to hit a 6-month release schedule where we do a year, kind of TikTok style release, where we do a 0 release that we support for a year, and then an intermediate 0.1 release which we support for 6 months to give us time to make some more changes, give the changes some time to bed in before doing another 0 release, which again we support for a year. As you can see by some of these actual dates, our accuracy is a little bit off on our 6-month schedule, especially 2.1, but we will not mention the 2.1 release cycle because I don't want to talk about it. Finally, the biggest change is formalization of our affiliated package review system. We currently have 8 affiliated packages listed. The review system grades the affiliated packages on a traffic light scale, red, amber, green, and on a variety of criteria, which you can see on the sunpy.org website. If the criteria aren't all met, then package can be listed as provisional. In addition to this, the affiliated packages which are maintained by the SunPy developers are nicknamed sponsored packages, and that's a list of all the sponsored packages. So quite a lot of the feature development that's ongoing in the SunPy ecosystem at the moment is happening in affiliated packages where new things are being added there. And finally, here is a list of some of the things I expect us to be working on in the next little while. As always, predicting the future is hard, so no promises, but we've got a major rewrite of NDCube coming out. Eventually, one day I'll actually finish it. Once we've done that, we plan on making map subclass from NDCube to benefit from a lot of the work that's been done in NDCube. The way we handle metadata and modifying metadata in map is massively overdue a rework, although it has had some small updates in 3.0. Adding functionality for regridding images to co-align them based on metadata hopefully will be made easier in the future. And as I said, a lot of the work at the moment is going on in affiliated packages to make them better and make more of them. So yeah, that's me.
I'd encourage anyone to ask questions quickly if you got them. Otherwise, we can move on to PySat.
I have a quick question. So I know SunPy has Google Summer of Code students, or has had them in the past. Are there going to be any this year?
Probably. We are participating in the program. We have asked Google to grace us with students. So we will probably have some, but they have not been selected yet. So I can't say, although I know the answer, I'm not allowed to speak the answer to tell you how many or who they are.
Okay. Thanks.
All right. Stuart, if you could stop screen share, then we can move on. We've got PySat up next. I assume Russell is taking that one.
Good afternoon, everybody. And thank you to the PyHC for giving me a chance to share about PySat again. So this talk is titled The Bridge Between Worlds. And of course, I'm representing the PySat team. So that's me, Angeline Burrell, who's now at NRL, and Jeff Kleinstein, who's at NASA Goddard, and also Jonathan Smith has been contributing more. So I'd like to start just by describing the general problem space that PySat is trying to go after rather than jump into specific features. And then the challenge that we kind of face in space science and a number of other fields is that we have a lot of different data sets that we're trying to get access to, each of which is generally in a different data format. Different sources have different metadata standards. There's a range of dimensionality that we have to deal with, 1D, 2D, 3D, 4D, hopefully not more than that. And to really analyze all the different types of behaviors we're looking for science, we need systems that can handle, all that dimensionality, hopefully within a single framework. Data sources, data all comes from different places. The data itself comes with different cleaning standards applied, or maybe different levels of flags, things like that. So sometimes it's incumbent upon the users to sort out what is good data versus not so good data. And solutions to these problems historically have been, institution or research group specific. Whoever happens to get funding for a particular problem, right? They begin to develop some tools, and then usually those tools can help them, perhaps get more funding in those areas. And then before you know it, a certain group has, a history and more access to particular things, and perhaps, a new group coming on. And historically, these have not been shared so much. That's not been required by government funding. And domain-specific problems, just for space science, not all scientists are trained programmers. Usually the focus and wherever school they're at is going to be on the space science part of it. of course, which makes sense. But at the same time, to advance space science, data analysis is required. So a lot of students end up with practical knowledge, but may not actually spend time on some of the fundamentals and fully appreciate, perhaps a single subtraction can really ruin your day in terms of precision, even though the program will still continue to run. And historically, publications themselves, science is discussed and evaluated and plots. But the code that actually generated those plots isn't technically reviewed. So we, just as a community, we aren't really aware of what, what kind of code has generated the results that we incorporated into our view of space science. And some typical things that make science different than perhaps some other fields is that there's generally shifting requirements. The project might start with a general idea and then you drill down, or you might be doing one thing, and while you're doing that, you might notice something a little funny, and then you switch and you look at whatever's going on over there. But even if we're at the interactive stage down towards near the end, when we have a very good idea trying to make our publication plots, we need results, robust results at each stage, and whatever modifications we do for a unique analysis really need to be portable so we can build on them or be released to the community. So PySat is our package that we're trying to that we're building to solve those problems. It stands for the Python Satellite Data Analysis Toolkit. It kind of works as an acronym and thing, but it's not really just satellite data anymore. It's ground-based data, it's model data, it's all kinds of things. And then the main goal there is to provide a simple, flexible, and consistent interface to any data set. And we're focused on space science because that's what I work on as well the other PySat developers. But the kind of approach that we put in place here will scale to other fields. So there's generally a lot of specifics if you're going to do a particular data set, but in the general, setup for data analysis, there's common things. You have to download the data, you got to organize your files, you have to be able to load the data, clean it. Usually there's going to be some modification or some unique processing, custom analysis that's added to it. You have to, bring in other packages for support. And then you might have to do some instrument specific analyses, but with PySat, you can generalize to do just, create an analysis that's instrument independent. So the main way to get generalized access to data is through what we call the instrument object. It's our primary user interface. And we've just got 4 degrees that you can drill down to any particular data set from platform, like, the name of the satellite, the name of the radar, name of the instrument. Instruments tend to have different levels, or instruments might have a range of data products. So we've got a tag for that. And then, there could be a constellation instrument ID. First step is usually downloading data. So we've got, systematic interface to all aspects of working with the data. So as part of the instrument object, if you want to download data, it's always the same way. You invoke the download function. We also have a little fancier routine that's download updated files. And what this does is it looks at what files you have on your local system. It goes to the remote server, figures out what files are on there, parses all the file names to identify what day those files are, what version, what revision, even down to a cycle. And if there's a newer one on the server, then it downloads it to the local machine. Here's just an example. I grabbed this out of one of the pull requests that were done. So all of our code gets reviewed by somebody else. So I reviewed this request here, which Angeline Burrell added some support from Madrigal database for vertical TEC from GNSS, the TEC instruments. And this was just, I downloaded the data, just grabbed a random day and did a plot just to make sure I could, download the data, load the data, plot the data. In this case, we are exposing an X-array data set object because this is a multi-dimensional data set. We also support pandas data frames. So new in version 3s, we actually support loading more than one day at a time. Previously, PySat was optimized for a single day, and now it's been generalized across all instruments for loading arbitrary ranges. So here's just a simple example. This is from the gold instrument. So the instrument instantiation was before, but all the data just ends up attached to .data, or we also provide, label access and stuff here. So the whole point about PySat is presenting data to the user. So we want to make that as simple as possible. In this case, we're just selecting the first time slice, and this is just showing some kind of raw outputs from gold. Just an example from Hickamarka to show that we have it. All the data is in .data. So we create an instrument for Hickamarka Radar Observatory, download between the 2 dates, load for a particular date, and then we just wrote a simple plot routine that accesses all the data in JRO.data. So I also have custom iteration by orbit. So this is a general PySat feature. It doesn't require any support from a developer who's adding an instrument. What it does is it allows you to paginate through the data on arbitrary conditions. So in this case, I'm an ionosphere guy looking at plasma drifts. So what works well for me is looking at drifts in magnetic local time, because plasma is controlled, strongly by the magnetic field. But orbits themselves don't care about, file breaks or day breaks or anything like that. So you can tell PySat, hey, I want to iterate by orbit, and PySat itself will go through and load a couple days, figure out where the first orbit actually is. So, in this case, the first orbit added the date, started the day previous. It loads the day previous here. That's this load here, and then goes back to the day I've actually asked for, day 2 of 2010. So this is just showing the UT that it actually automatically joined these files, and then showing this in the preferred view. In this case, I asked for orbits by local time. All right. I just thought I'd show this code. Actually, this is one of my first examples that I ever showed for PySat. This code actually still works despite the multiple releases we've had. Here's an example for a more modern or more recent data set. This is for ICON. So this is a higher dimensionality data set than the in situ parameters I was just showing before. These are remote optical observations of neutral winds. This is ICON satellite MIDI instrument. MIDI measures temperature and the winds. So I've got some temperatures over here, and there's also EUV instrument on there is measuring O+ density. So here are the altitude profiles we're getting from there. And this is broken down by orbit as well. So I'm using the orbit iteration here to go through custom on the ICON data set. And what's important is this is all done in real time. So a particular data set doesn't need to have like an orbit number. You just need to say, I want to, it's got polar orbits, local time orbits, things like that, equatorial crossings. It's got a few orbits that are built in. So I wanted to provide a quick example of loading multiple days. So this is all backwards compatible. Before you could provide the year and the day of year, and it would load that single day. For F10.7, which only occurs, that measurement's only provided once a day, you get a single number out, and that doesn't seem too impressive for what's supposed to be a fancy package. But now we've extended it. You can do range of days, year days like this, and now it's backwards compatible with these keywords, or you can do range of dates or ranges of files. It'll load all that in a systematic way. So I'm just showing F10.7 here, which is a simple data set. But again, this is a systematic functionality. So if you said load 50 days of TIGCM model data, it'll try to do that too. There we go. We've got built-in support for cleaning and modifying data, because generally you don't just want the data, you need to modify it in some way. So we've got the ability to add custom functions to the instrument object. And whenever any routine invokes a load on the instrument object, these custom functions automatically get applied. So this is important for instrument independent functions, like say I've got a seasonal binning routine, but I need to average a parameter that's not actually in the file. I need a calculated parameter. Well, with this functionality, I can attach this function to the instrument object, and then when I pass the instrument object over to the analysis routine, the instrument object itself knows what to do. It modifies the data as it's been instructed, and then that new parameter, whatever you add, is going to be available to that binning routine without having to mess with the analysis object. So in this case, I'm just doing a trivial example, double F10.7, but it comes out. And you can access, in some cases, if it's appropriate, we've got data frames, pandas data frames for higher order data. We're on X-array now. PySat itself also checks the data as it loads and stuff to make sure things are good. So, and we've upgraded to using logging functionality. So in this case, you can see some user warnings are popping out. This is a development data set that I'm working on, but it's letting me know, hey, there's an issue with the times, they're not unique. It's also letting me know I didn't finish with the metadata. To actually load this stuff, I also had to disable a particular flag for that check. You can access the data. The whole point about PySat is to make it easy for scientists to have like unmitigated access to the data set. So things are actually just like attached.data, or we've support normal kind of NumPy type access things that you'd expect here, range of date times, index arrays, slicing, things like that. We've got support for metadata, and it works for different labels depending on institution, and PySat will actually transparently handle that mapping for you, and you can define that quite easily. But it makes it possible to write code that interacts with types of metadata without having to know what the labels are. So that's pretty nice. And for each instrument, now we support acknowledgements and references because we, scientists will need to know where these things are coming from. So the instrument object itself, am I out of time?
Sorry, let's try to keep this to a few more minutes.
All right.
Thank you.
All right, so the instrument object itself has a complex data flow for all these things that occur, which enables kind of arbitrary relationships between the data as loaded and the data at rest in the file, but it's very systematic, and we've exposed things, the right types of functions across the level to enable whatever kind of modifications you need to do to integrate a particular data set. And one of the biggest things here with the PySat 3 release is we've built it so you can build packages on top of it. So we are in the process of building an ecosystem of things. So PySat becomes the core, and different data sources become, different data sources become the like penumbra of packages around it that are for, PySat models is for model data, and that PySat NASA for NASA. So you can build whole entire processes based on PySat. And for that, we've got lots of documentation, tutorials, API, how to add an instrument, all kinds of good stuff. We have really high testing. So here's all the packages that we've got. We've got a variety of data sources over here: NASA, CDAC, Madrigal from NSF, PySat space weather indices, models for model data, missions for planning missions, simulating missions, all kinds of stuff like that. Loading CDF files, seasonal bin analysis. There's going to be, I think, a talk about Komodo. Well, Komodo and PySat have been connected together. So all the data sets that PySat has with Komodo can now kind of get for free. And PySat tutorials is there to provide some examples. So all of these penumbra of packages are still in development. They used to be in PySat, we've broken them out. And PySat 3 has been officially released a couple months ago. And now we're getting all the penumbra consistent with that for their own official release. We have a lot of instruments. This isn't all of them. I ran out of space. But PySat's in use for ICON mission, Cosmic 2, CubeSats, as part of a DARPA funded project to integrate a whole bunch of different data sets together for a space weather prediction model. I'm using it to couple new basis vector system I've created for ionospheric ion drift analysis, mapping of E fields and stuff. So PySat couples that package to those missions easily. All right, so that's it. Version 3 is released. It's up on GitHub. The whole ecosystem is just under PySat. We're open to community development, and here's the GitHub. You can post issues if you have problems. We've got milestones for our upcoming development. So we're trying to be on the ball in terms of community standards and open development. So thank you very much for the opportunity to speak today, and sorry if I went a little long. Oh.
One quick question, anybody?
I have a quick question. Does PySat support Windows yet?
Yes. So we're hoping to get more Windows testing. So, as nothing breaks that we know of, but it should work on Windows. Generally, so one of the biggest things, we removed the PySat CDF requirement, and that generally had that was always the stopping block for people getting that going with the compiling with Fortran and other things, particularly on Windows. So now the requirements are much less, and the only things on there are Python or super well supported stuff. So PySat itself should load up on Windows without any issue whatsoever, as far as I know.
Cool, thanks.
None of the development team uses Windows, so we are eager for some Windows users to report back.
Hey, thanks, Russell. This is Asher. Just to comment on that, we we containerized PySat at some point for the PySat Komodo stuff. So if you're on Windows and you have Docker installed, it's pretty straightforward to run a container including PySat and then mount your data directory into the container so that it basically lets you kind of avoid any dependency conflicts that you might have with your Conda environment or your Python environment.
Great, and with that, I think it's time to move on to the next presenter.
I think that would be me. So let me try to share my screen. And can everyone hear me okay?
Yeah, you're coming through fine.
Okay, great. Let's see. All right, so I'm going to be giving an update on PySpeedS. So we're still using the MIT license, so all of this is free open source and can use it for anything. We dropped support for Python 3.6, mainly because NumPy and Xarray and most of our dependencies are dropping support for 3.6. And we added support for 3.9. And we currently support Windows, Mac OS, and Linux. There were some issues with Windows earlier this year with NumPy, and those issues have all been worked out. And so we're back to supporting Windows again. And we're distributing through PyPI. So it's just pip install PySpeedS and -- upgrade to get the latest version. We started off using Anaconda as well, but that became too much of a hassle to actually maintain two different distribution platforms. And PyPI seems to work across all platforms. And so we dropped Anaconda and we're just focusing on PyPI for distributing PySpeedS. And so now we support loading data from 24 projects and over 135 instruments. And I call them projects here because it's not just missions. It's we also have ground mag data, magnetic induction coil array data. So there's other data types other than actual missions. Data sources include the main one is NASA SPDF. We also support LASP, grabbing data from LASP for MMS and Maven. So that's especially like the team only data for MMS. It all comes from LASP. We also support grabbing data from UC Berkeley. So that's the Themis data and the stereo, mag, and plastic data. We also support ERG data from the ERG Science Center. So that's ARASE. And data from UNH, that's the magnetic induction coil array data. So that's ground data, as well as grabbing net CDFs from NOAA. And right now, that's just mag data, but I'm planning on adding the particle data, the GOES particle data, as well as the GOES X-ray data. And all this is from a simple, easy to use interface. It's just PySpeedS.mission.instrument, and those are functions, which then take options via keywords. So you set the T range, the level, the data type, and all of those have defaults for each instrument that should load some data. So for instance, to load MMS FGM data, it's just you import PySpeedS and type PySpeedS.mms.fgm, and it'll just load some data. And we also have additional analysis tools. So we have coordinate transformations, we have dynamic power spectra, wavelet transformations, as well as tools. We now have tools for creating spectrograms from plasma distribution functions, plus a lot more. These are really just the main ones. So here's a list of all the missions that we currently have. And in the presentation, they're clickable, but the easiest way to get to documentation is just to go to our GitHub page, and in our README, we have a link to each one, to each mission, which you can then, for instance, go to MMS, and we have documentation on what's available here for MMS. So we have all the instruments, all the levels, all the data types, even the team only data, even the ASCII data. And we have a bunch of flexibility. We have the ability to set mirror data directories. So if you have a network mirror, you can copy the data locally off the network mirror and grab the data from there. And this is all stuff that was requested by the team. And we have all the science quality data products. That's for FEEPS, EIS. I think we were missing one routine for EIS, but a contributor from the EIS team actually just recently gave us that routine, provided that routine. So now we have, should have pretty much complete support for MMS, at least for loading the data. And that's including post-processing. And so let's go back here, full screen. So the load routines support local caching. So we cache the data locally, and if the files don't change remotely, then it just loads the local files. We also support temporary files. So if your internet drops out while you're downloading data, it doesn't actually try to load a broken file on. We also support, of course, loading files without an internet connection, and there's keywords where you can tell it not to go out and grab the data remotely. So there's also a no update keyword. For all the load routines, we support downloading the files without actually loading them into memory. And there's a keyword called download only. It just grabs the files, and we support usernames and passwords. Right now, just using standard HTTP authentication. This was big for some of the mission teams like Arase. They keep their team only data behind a username and password. So pretty much had to add that. We also support loading the files into NumPy arrays without actually creating PyTplot variables. So there's a no tplot keyword on all the load routines, and that'll just cause the load routine to create a hash table of hash tables. The top level, it just has the keys or the variable names, and those map to a hash table containing the times and the data values, as well as, and it supports multidimensional variables. So if there's an energy table, it also includes the energy table. And we have a detailed getting started guide available for MMS. Although it's useful for other missions as well. I primarily made it for MMS because users, that's really where we started. Let's see, I have an example of that over here. It includes things like setting up the virtual environment, installing an Anaconda, setting up the virtual environment, installing PySpeedas, setting local data directory, setting the network mirror data directory, making sure everything works, and then where to find more examples. We also created getting started with PySpeedas on Windows for a meeting earlier this year, and that walks through getting started on Windows. And we recently gave a presentation on contributing to PySpeedas to the Arase team. And this is mostly geared towards IDL developers who haven't actually, who aren't familiar with Python, but want to get started with Python. And we include things like how to create a fork, how to actually submit a pull request, because they're fairly new to Python. So we wanted to create detailed instructions on how to actually contribute. And I mentioned we have coordinate transformations now. We now support GEI to GSE and back, and this is a true update GEI. GSE to GSM and back, GSM to SM and back, and then GEI to GEO and back, GEO to MAG and back. And then the true update GEI to J2000 GEI. And all of this is just porting our IDL transformations over to Python. And we also have GSM to element. So that's boundary normal coordinates using the SHU magnetic poles model. Again, it's just a port of the routines from IDL. And as I mentioned earlier, we also now have particle tools for creating the energy, theta, and phi spectrograms from plasma distribution functions. And the input data structures and the routines are almost identical to our IDL data structures and routines. Pitch angle and gyrophase spectrograms are coming next. This is really just a matter of doing the, because of the way these routines are implemented, all we have to do is do a field align coordinate transformation here, and then we can use our theta and phi spectrogram codes to can then generate the pitch angle and gyro phase spectrograms. And this currently only supports FPI from MMS, but we have we're going to be adding HPCA and then THEMIS, ESA, and SST really soon. Since these routines are generic, it's just a matter of writing a routine that reads these plasma distribution functions into a common this common data structure. And speaking of that data structure, we're going to have proper documentation of that data structure soon. It's fairly straightforward on how to do it, and it's just a matter of actually writing out the documentation. And we also still really need to add a lot of documentation to the routines. I think most of our plasma routines just have empty doc strings at the moment, because I've been mostly focused on validating that they actually work. For examples, we now have around 20 Jupyter notebooks containing examples from loading data from MMS and doing analysis on MMS data and THEMIS. Our examples are stored in their our top level repo. So it's just, you just go to the SpeedS organization, and we have MMS examples for all the MMS examples. I think the THEMIS examples and more generic examples are under PySpeedS examples. Just as a
Wait. Hello.
yes. So I'll show an example of, let's say, calculating plasma beta with FGM and FPI data. It's just a Jupyter notebook where we show how to load the data and then interpolate the data into new timestamps. And what I did essentially was take a crib sheet that we have that we created in IDL, and then recreated the crib sheet as a Jupyter notebook in Python. So this is essentially exactly what we also have in IDL. And it shows how to store the data and create plots. And we have lots of examples. It's just a matter of clicking on the data product that you want to see how to create that data product. And we have more examples are coming soon. We don't have examples of the coordinate transformations yet or the particle tools. And there's a lot of analysis tools that are missing examples in notebooks. So I think we're going to be working on some of those during the hackathon on Wednesday as well. For unit tests, we're currently at 82% test coverage, and we're using GitHub Actions to run the full test suite on every commit to the main branch. And most projects are well over 90% test coverage. I think Maven is pulling us down. It has some large files that we still need to add tests for. And we're using coveralls.io to measure the test coverage. And setting all that up was super simple. Really, this is super useful because it shows you on a file at the folder level as well as at the file level what the test coverage is. So you can see most missions have above 90%, except Maven. You can see there's some large files in here that don't have test coverage added yet. And in addition to the actual unit tests, so these are useful to make sure that things are technically working, as in you can actually load data and it's loading it into memory. But we also have validation tests and these are implemented in IDL. So these are unit tests that load the data in IDL and then load the data in Python and then check that the data products actually match. And here's an example just for our MMS tests. So we load the data in IDL, and then we have a routine called SPD run Py validation, and you give it the script as a list of commands, and then you give it a list of variables to check, and it returns 1 if they match and 0 if they don't.
Giving you a time warning here, we're getting close.
And for future plans, we still need to implement a happy client. So this is to bring happy data into PyHC plot variables. We still need to add barrel data I think someone recently asked about barrel data. I think the barrel team is interested in bringing their data products in as well. And we have a lot of post-processing coming. We're adding Themis calibration routines. So it's starting with the FGM calibration of the L1 data. The Arase team is soon going to be adding more post-processing for their data products. And we're going to be setting a lot more plot metadata on loading the data. And we have more analysis tools coming. We're going to be making our particle tools available for more missions and instruments. As I mentioned earlier, it's just a matter of implementing the reader for different instruments, which can then we can then use our particle tools right away. And then we're going to add slices of the distribution functions. And we need to create more examples, and we're going to be giving more webinars. There's actually another webinar coming up really soon for MMS data and PySpeedS. And we really need to improve and automate our documentation. As I mentioned, right now we're doing most of our documentation as doc strings, NumPy style doc strings, and we're using our READMEs for high-level project documentation. For both the top level as well as individual instruments like MMS. But it would be really nice to set up Sphinx and put together a read the docs for PySpeedS, but we're not there yet. So that's all I have. Questions?
Yeah, I have a quick question. So I was wondering, kind of on a project level, what drives the instruments you support? So is that like whatever the developers are interested in, or do you have like specific funding for different instruments? Or
so well, we want to support as many as possible, and but I tend to triage things based on user requests. So if someone requests something, then we give it a higher priority. Right now, the big request is all particle tools. People really want to do slices. People have been requesting that for a while now, which is why we're focusing on that. But we do have funding from MMS to provide support, which is why we're at such a high level of fidelity for MMS data. And we also had support from NASA for general SpeedS.
All right, well, we do need to move on to Brian.
Can I ask a quick question to Eric?
Yeah, go for it.
So I'm used to SpeedS and I'd like to try PySpeedS. If I'm used to using a routine in SpeedS and I learn how to use it in PySpeedS, should I expect that basically whatever I know exists in SpeedS is translated into PySpeedS?
Yes. Though I would check the doc string first, just to make sure.
Okay, thanks.
Yep. All right, thank you.
All right, I'm up next. I've got two project updates, but I'll go through them pretty fast. So I'll be updating on PyTplot and CDFlib. I'm Brian Harder, for those that don't know me. It's been a while since I've been at the these conferences, though I drop it on the telecons periodically. So it actually has been about, I was looking, I think it's been like 2 years since I've updated on these libraries. So there's quite a few list of updates on certain things. So let's see. So first I'll go through PyTplot. So a little bit of background about PyTplot. Its scope and goal is to provide similar functionality to the IDL tplot library, if you're familiar with that. And basically what the IDL tplot library does is provide this common data storage item, read in data into that common data storage format, and then easily plot like these publication quality stacked time series plots based off of the data in that common data model. The PySpeedas library, which we just heard about, uses PyTplot on the back end, I think, for the data storage, and a few of the routines for loading in data. In general, though, PyTplot is focused on the data storage level, the data model, as well as the plotting routines, whereas PySpeedas is like all the download routines, all the analysis routines, all the kind of heavy lifting stuff, where PyTplot is kind of more focused on plotting and the data model. So in general, the typical workflow with PyTplot goes something like, read in the data using the either loaded in directly using a store data routine, grab it out of a CDF file, net CDF files, or even IDL save files, because there's a library that'll allow you to convert IDL save files into Python dictionary objects. And then it provides this simple interface for saying, alter this part of the plot, say, options, the space between plots is this much, and it has this subtitle, or, just this kind of simple interface for changing the options of the plots. Then doing some data manipulation if needed. Like I said, that's kind of been more the area of PySpeedas lately, doing the data manipulation routines. And then finally just clicking, tplot, generate the plot, and then you get this publication quality plot. So recent updates. So over the last 2 years, pretty much, because it's been that long since I've given an update. Right after the last Helio Python conference that I attended, PyTplot started using the Xarray library rather than pandas. What I was using before was this common data model called a tvar, or a tplot variable, that had a few different pandas data frames in it, as well as like some variables for metadata. But I just went and simplified all of that. So now all that happens is the tplot variables are just Xarray data objects. So that stores, all the kind of coordinate data, all of the metadata attributes, and it's been great. I think it's worked out great so far. Added a brand new readthedocs.io page. So now the reason why I kept it in not presenter mode was so I could drag things over here. So we've got this read the docs page, and I found out, you can actually add interactive plots embedded into read the docs. So that's been kind of cool, just having these HTML plots do stuff. New plot configuration options, just some random ones that I saw while looking through the Git repo. Now have scatter plots. You can change the vertical spacing between plots, change the background color, subtitles, disabling the y-axis zoom. I mean, the full list of available plot options is available on that Read the Docs site, but these are just some of the newer ones. You can read in and import STS files. I don't even know how common they are, but they're used on Maven. I think that stands for simple time series. It's literally just a giant ASCII table formatted some certain way. But that'll read it directly into the Xarray object. You can import without graphics. We started using GitHub Actions to do all of our unit tests and pushing to PyPI and Anaconda, which I'll talk about more tomorrow in the demos, or rather the tutorials. New interactive plots. So I went and added in a 2D and 3D position viewer. If you scroll over the mouse and you have position information linked into that variable, saved into the coordinates of that variable, then it'll update a little 2D or 3D position over a planet, which I had loaded up already over here. So this is basically all done in PyTplot, but I did a little bit of work to merge the windows together. But you can scroll over the plot, the spectrogram plot here, and it shows a bunch of different interactive type plots. So like the bottom left one is a map of, this is Maven data. So this is a map of Mars and where the spacecraft is located over it. We've got the actual slices of the spectrogram data in the upper right corner, and then position data in the bottom right two visualizations there. Okay, moving on. I put that there in case the demo didn't work. So libraries used, like I said, we're using Xarray. That's the primary data storage object. And like I said, it used to be pandas, but Xarray handles multidimensional data much, much better, and also has the capability of putting in the metadata attributes right next to the data. PyQtgraph is the primary plotting library. Supposedly it's faster than matplotlib for large data sets. I've never done any formal testing on it. But I personally found PyQtgraph easier to customize, and by default, it looks a lot more similar to the IDL, what IDL tplot generates. So if for people that are familiar with tplot, I think PyQtgraph kind of looks a lot more similar. Bokeh is the HTML file plotter. So it actually generates HTML files and creates plots that way, which is technically still supported. It still works, but a lot of the newer features that I've added don't work with it. A lot of that is because I don't actually know anybody that's still using the Bokeh version. A lot of people are just exclusively using PyQtgraph for plotting. And it is quite a bit slower than actual PyQtgraph. So in terms of future plans, so I haven't had a whole lot of time to work on these Python tools, not as much as I would like. I've been quite busy with the Emirati Mars mission. So I recently gave admin privileges to the repo to the PySpeedass developers. At least I think it's admin, or whatever gives them permission to kind of do merges to master and push to PyPI and Conda. And what I've been doing is basically, as you know, I've been getting bug reports or feature requests or anything that's can be done quickly. That's kind of what I've been focusing on while I've also been busy with the EMM mission. And I really need to get done the project self-eval and add examples to the HelioPython site. Since there's only 5 minutes left, I'll just skip right ahead to CDF lib. Any quick questions on PyTplot? All right. So CDF lib, I see that there's been some chat about that in the Zoom chat room. I haven't been keeping up. But anyway, it's just a pure Python CDF file reader and writer. The functions within it for reading and writing data is very similar to the stuff found in IDL, because that's what I personally was familiar with when I started writing it. But it's had a lot of contributors over the last 3 years. I know it's currently being used in PySpeedass and HelioPy. There's a brief history there, which I won't go over right now, just in the sake of the interest of time. But yeah, it's been quite a few contributors. So recent updates, the last 2 years, the core pieces of the library, they've remained very similar. The back end is even similar. A lot of the updates are more, they've been kind of focusing on refactoring the code and error catching and bug fixes and stuff like that. David Stansby's co-owner of the project, so also has admin privileges, ability to push and stuff to PyPI. So he's been working on, you know, bug fixes, feature requests as they come in. I've seen a year or two ago, Michael Hirsch contributed a bunch of code. You know, he actually got it using GitHub Actions for unit testing and pushing and stuff like that. So that's where I learned how to use GitHub Actions. I saw what he did and was like, oh, that looks great. I'm going to use that for PyTplot. And then I'm giving a tutorial on it tomorrow. And Mike also went through and did a lot of refactoring and reformatting of the code. I saw David at some point went through and sped up the epoch time conversion libraries, routines. And at some point, I added the option for using AstroPy time for the time conversions, as well as the option to convert the epoch times into just AstroPy time objects. So future plans. The documentation needs definitely an update. It all currently exists, but it's all basically in one giant README file that you can see on the GitHub page. So you go to the GitHub page under Maven SDC/cdflib, and the entire bottom, like 90% of the page is just all the documentation shoved in there. So it'd be nice to get that and read the docs. And then also, I had a small proposal accepted in the for this year from the HDE EE calls to upgrade CDFlib to read CDF files directly into Xarray objects, and then also take Xarray objects and convert them directly into CDF files. And there's details here about exactly how that was going to happen. But I also went over that in a meeting a couple weeks ago, so might not need to go over it again here. Plus, there's also only 2 minutes left in the talk today. So, yeah, so that's what I had. Any questions?
I have a question.
Yep.
What is the advantage of using the X-ray? What does that buy you?
Yeah, so I was using pandas a lot in PyTplot. Pandas was really optimized for only, basically 1D data, 2D data. But Xarray can handle any sort of amount of any sort of multidimensional data. What I really like, it's kind of minor, but you can store metadata in the actual Xarray object. So there's different attributes that you can just add to the data, and then various routines in PyTplot just read those attributes and say, oh, this data variable should be, have a, when you plot it, it should have a log on the y-axis, or when you plot it, here's the variable labels to use. So it's just kind of helpful there. For those types of things, for storing plotting type information, but it also stores coordinate information, which is handy because there's certain built-in routines that can use the coordinates information of the data. So you can say like, here's your data cube object, but its coordinates are these other data cube objects here, or this data array object, and say like, okay, time, these time variables represent this axis, and these are the bin data up here. And then there's routines to interpolate or resample, or just kind of nice helper routines that help with the coordinates.
Okay, thank you.
Yep. All right, any more questions? All right, I'll stop sharing.
Thanks, Brian.
Yep.
Awesome.
Yeah, thank you, Brian.
All right, with that, we wrap up for today. We'll start again tomorrow, same time, 9 o'clock Mountain Time. And tomorrow we're going to start off with tutorials. I believe our first one is the Python for IDL developers from Eric. So if you know anyone who you want to support in their transition to Python, let them know they should call in. They're welcome to join us. I've saw that most everybody has already uploaded their presentations to the Google Drive, so thanks very much. And unless there's any other questions or comments, we'll wrap up and I'll see you all tomorrow.
Yeah, just a reminder that by 9 a.m. Mountain Time tomorrow is when we'd like to have you all upload your things to the Google Drive. And yeah, thanks so much. I don't have anything else, Alex.
Awesome. All right, I will stop recording